Alright, so I want to show you a real world example of a hyperbola. Um, and that's one of the conic sections here. Here's a diagram of a hyperbola. And the definition of a hyperbola is it's the locus of all points, the difference of whose distances from two foci are equal. Um, and that sounds pretty abstract and weird or whatever, but actually things in nature follow that pattern, and one of those things is um, uh, a comet. Many comets will take a hyperbolic path around the sun. Some comets travel in very large ellipses around the sun, but sometimes comets come in other words, so they keep orbiting the sun in very very long periods of Halley's Comet comes back every 75, 76 years. Although, by the way, that might have hit some other comet and exploded, so it might not come back. Hopefully, it does. Um, but some comets just come into the solar system and then leave. They're gone. They follow that hyperbolic type curve. So I've got just an example of a comet here with some two pieces of information about it. And we're going to see if we can take those pieces of information plus what we know about hyperbolas, um, plus a couple other little formulas that I have that help us get some information, and then see if we can write an equation that approximates the orbit of this comet. So okay, so the orbit follows just one part of the hyperbola, the geometric hyperbola. So, like just one of these curves, not both of them. I mean, that'd be pretty cool if it would swing in and then whoop, just flip over, and I don't know, or if there's like some doppelganger comet. Anyway, I'm getting off tangent here. So it's following the one of these curves, um, and the focus then is the sun. The focus of that curve is the sun. And what we have here is the perihelion, which is the shortest distance between the comet and the sun, the closest it gets to uh, the sun. And for this comet, it's zero point 0.5 astronomical units, AU. An astronomical unit is defined as the average distance of the Earth to the Sun, so roughly 93 million miles. So this would be a typical comet would let's say come into the solar system, and it would swing around the sun, and at its closest point it would get to about half the distance of Earth to the sun. So 46 something million miles to the sun, let's say. Um, so that's one piece of information, the perihelion, its closest distance, and then another piece of information is the eccentricity of its orbit. And eccentricity is basically a measure of how far a curve deviates from a perfect circle. A circle has an eccentricity of 0. A parabola has an eccentricity of 1. Ellipses have eccentricities between 0 and 1. And then hyperbolas have a eccentricities of greater than 1. So for this one, it's 1.3, and we can use that information here shortly. So here is the equation for a hyperbola again. Here, x minus h squared over a squared minus y minus k squared over b squared equals 1. So let's see what information we need. First of all, this hk business is just if the hyperbola is not centered at the origin, 0, 0, hk would be the coordinates of the center. But we're going to say, because we're going to say our coordinate system here in space is such that this the orbit of this what's this called, comet, is centered on the origin. We're just saying that. So what we really want is x squared over a squared minus y squared over b squared equals 1. So we need a and b. Well, what do a and b represent? Um, well, a is the distance from the center of the hyperbola to the vertex, and c is the distance from the center to the focus. So I'm going to actually draw a here as well. Because what do we have here? We have the distance from the focus to that closest point. Um, right? What we have is this. Let's see. We have this distance. This distance corresponds to this. Um, and so, in other words, if you take c minus a, we get that. So let's write that. So c minus a is equal to 0.5 astronomical units. And we'll do all this in terms of astronomical units just to keep the number simple. So c, this distance minus this distance, is what we're saying. Okay. What else do we know? We know the eccentricity of the orbit of the comet. E is equal to c over a. That's just that's a way to define the eccentricity of that orbit. It's c over a. So we know what E is. It's 1.3. Okay. So, okay, we've got a little simple system of equations here. And what we can do is we can solve for a and c. If we know a and c, we can use this relationship, c squared minus a squared equals b squared, to figure out what b is. Then we'll have a and b. We'll be able to write our equation. Okay, let's rewrite this as, I'm going to multiply both sides by a, so that 1.3 times a equals c, and I'm going to use substitution to solve for a up here. So if c equals 1.3a, then I'll just put 1.3a here. So 1.3a minus a equals 0.5. So 1.3a minus a would just be 0.3a equals 0.5. So and then we can divide both sides by 0.3. 0.5 divided by 0.3. So a is 1.6 repeating. Let's just call it 1.7. So a is 1.7 astronomical units. Okay. So the distance from the center of this hyperbola to the vertex is 1.7 astronomical units, so 1.7 times as far as the Earth is from the Sun. All right. And now, let's see. So we can use A to solve for C. C, let's see, what would be the easiest way to do that? 1.3A equals C. So we could take that times 1.3, and that'll be C. So times 1.3 is 2.16 repeating. Let's call it 2.17. All right. Hopefully this is not getting too boring for you. Point being, we can take some simple information about a comet, the eccentricity of its orbit and its perihelion, and we could work out an equation for a hyperbola that describes its orbit. Okay, so we're almost there. Hang in there. Okay, so c squared minus a squared equals b squared. So write that. So we know c now, 2.17 squared minus a squared, 1.7 squared, equals b squared. Once we've got b, we'll be golden. Okay, 2.7. So 4.69 okay, that's 1.7 squared, 1.7 squared, 2.89 is equal to b squared. So let's do, what was that? 4.69 minus 2.89. This is 1.8 roughly. 1.8 is more or less is b squared. Now let's just leave it as b squared because that's what we need for our equation. Um, okay. So and we've got what? So one a is 1.7, so a squared is 2.89 AU. So that's all we need. So let's write an equation for this hyperbola. So x squared. Let's do it in a new color. X squared over a squared. So a is 1.7 astronomical units, and so a squared is 2.89. So over 2.89 AUs minus y squared over what is b squared again? 1.8 equals 1. So that would be an equation that would approximate the orbit of this comet. Of course, the orbit would be shifting slightly because of the gravitational force of the planets and stars and other galaxies or whatever. But this is a good approximation for its elliptical path. So um, we could actually use that to predict where it'll be, when it'll be, um, etc. All right, there you go. A hyperbola in the real world. Astronomy is awesome. All right, peace.